All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. First of all, thank you guys for being flexible today and meeting virtually. I know it was a little bit of a last minute change, but I'm appreciate you guys coming here on Zoom. I will be back in class on Thursday, just because Thursday is our ANSYS activity, our fifth one, and so I need to be in person for that one. So I'll definitely be back on Thursday, but today I appreciate you guys being flexible. Okay, so I'm lecturing from my home, and so I've kind of turned to the side here because my cat is kind of sleeping on that chair right there. You can kind of see. And so hope you guys are having a good evening. Okay, so the plan for today is we're going to finish up our lecture notes on transient FEA simulations, and so that's kind of the precursor for the activity on Thursday. Okay, so on Thursday our activity is going to be we're going to explore the dynamics packages within ANSYS a little bit, and so we want to make sure that we're kind of adequately prepared for that, and so we're going to talk a little bit more about that. Okay. So if that doesn't take up the whole time today, I'm guessing we're going to finish that part and maybe a little bit early. Then we're going to start our next topic, which is verification and validation. Okay, which is going to be a very important part of your final project. And so you would definitely want to make sure that we talk about that. Okay. Okay. Right. And so problem set one is out there. So I know I've gotten a couple questions on email about problem set one, just because today's kind of been a little bit hectic, just because I was at the hospital for a little bit, so I haven't been able to get a chance to answer those emails yet, but I did receive them, and so please don't email me again kind of telling me I'm a bad teacher or anything like that. So I did receive the emails. It's just I haven't had a chance to respond to them yet, but I'm hoping I'm going to get some time later tonight to do that. Okay. Okay. Right. So I think that's it for my announcements. Are there midterm exam. So our midterm exam is going to be next Thursday. Okay. Okay. So that's going to be the 16th of November. Okay. So that's going to be 9 days from now. So normally for my midterms, what I like to do is I like to put out a study guide about kind of a week and a half before the midterm exam. I was originally planning on getting that done today, but of course, things happened. I wasn't able to do that. But I am planning on getting that out to you by tomorrow morning. Okay. So the study guide basically is going to cover everything that you're going to be expected to know for the exam. Okay. And if you haven't taken an exam with me before, let me go ahead and break down kind of the general format of the exam. Okay. Okay. So generally what you can expect is you can expect there to be basically four conceptual short answer problems. Okay. And so that's going to be worth about 40% of the points. Okay. And then from there, you can expect there to be two direct stiffness type problems. Okay. And so those are going to be problems that involve springs, beams, trusses, 2D. They're definitely going to be 2D problems. And so you're going to have to go through the whole direct stiffness process. And so you're going to write out all the element stiffness matrices. You're going to assemble them, apply boundary conditions. Okay. But I'm not going to expect you to solve it. Okay. So of course, during the exam, you're not going to have access to MATLAB. You're allowed to bring a calculator, but not everyone's calculator has the ability to solve linear systems of equations. And usually at that point, it kind of just ends up being kind of busy work. So even if your calculator does have that ability, you're going to spend so much time kind of punching in numbers in the calculator and making sure that it's all correct that it kind of takes away from the rest of the exam. And so, for what I'm expecting you guys to do for the direct stiffness problems is basically take it all the way up until the point when you're about to solve, right? And so you're going to show me kind of the final global stiffness system with all the element stiffness matrices kind of assembled in the right places, and with the boundary conditions kind of inputted in there as well. Okay. And so these two direct stiffness problems, they're each going to be about 30% of the midterm points, and so together they're going to be 60% of the points. Okay. All right, question. So we don't need to solve for the displacement and the reaction force. That's correct. Yeah. And so what I just kind of mentioned about solving the linear system, that's exactly solving for the displacement. So you will not need to solve for the displacement or the reaction force. Okay. Okay. So look forward to the study guide tomorrow. So the study guide is going to give you kind of basically some guidance in terms of how you can study for the conceptual questions mostly. And then for the direct stiffness problems, I always tell people that the best practice for that is the homework problem set. Okay. So those are going to be your two main resources. In addition to, so the study guide will tell you kind of what conceptual concepts you need to know, but the answers to all those conceptual questions are going to be in the lecture notes. And so your main resources for studying for the exam are the study guide, the homework problem set, the lecture notes, and of course, the lecture, whatever notes that you already have from the lectures, and the recordings and the videos. Okay. Okay, so I'm gonna put out the study guide tomorrow, but that's generally what you can expect. In terms of what you can bring for the exam, you can bring a writing utensil. Okay. So pencil, pen, it doesn't matter to me. Okay, so the only thing I'd probably say no to is probably the blood of your ancestors. So please don't write the exam in blood. And so pencil, pen, whatever you feel most comfortable with. Okay. Okay, so you can bring a calculator. So a calculator will definitely be useful because there's definitely going to be a lot of kind of small algebraic calculations in the direct stiffness problem. So that's definitely good to have. And you can also bring a cheat sheet. So you can also bring a 8.5 by 11 sheet of notes. Okay. You can write on both sides. And you can write it or type it, kind of whatever you feel most comfortable with. Okay. All right, question. So will there be nodal and distribution problems? And so I'm guessing you're asking about the loading. You will, there is a high possibility for there to be a distributed load problem. And so you want to make sure that you know how to convert a distributed load to nodal loads. Okay. Definitely be prepared for that. Okay. Yeah, so the exam is going to take place during the lectures. Usually what I do for my exams is that I write up the exam and then I take the exam myself. That's mostly kind of catch any typos or anything that might be there. But it's mostly also for timing too. And so, usually for the exams, I try to make it so that time is not a factor. But with that said, with these exams for direct stiffness, traditionally, in the previous times that I've offered this course, students have kind of struggled to kind of finish it in time. Not because the content is hard, just because there's just a lot of writing involved in these problems. You have to write a lot of matrices, you have to write, a really big matrix, to make sure that things are going in the right place. And so, you want to kind of make sure that you're practicing a lot so that, it's a lot of these things are kind of automatic just because you're going to spend a lot of time just writing the matrices. And that's just the nature of these problems, right? And so, that's one thing I do want to caution you about for this exam. Okay. Your wrists are probably going to hurt after the exam because it's going to be a lot of writing. That's just kind of, there's just kind of no way around that for these kinds of problems. Okay. Okay. Anything else on the exam? Any other questions about the exam, the content, or the format, or kind of the logistics of the exam that I can answer right now? Okay. All right, and so definitely, you want to start preparing for that. Working on the homework problem set is definitely good preparation. Question, can we put anything on the formula sheet? You can put anything you want on the formula sheet. The only thing you can't put on there is the answers to the exam, which will hopefully be impossible because I'm going to take the exam and I'm going to take the answers and lock them up in my drawer. So if you somehow hack my computer and take the exam or break into my office and take the exam answers, then I guess you can, if you put that on your cheat sheet, that's bad. But besides that, there's no limits to what you can put on the formula sheet. Yeah. Yeah. So I know what some people like to do is that they like to take my posted lecture notes and then make it really, really tiny and put literally every single sheet of my lecture notes on their cheat sheet. So that's possible. You can do that. People have done that, but it's usually not a wise thing because I think you kind of spend more time trying to read the tiny print on your cheat sheet rather than doing the exam. And so you want to make sure you write your cheat sheet in a way that it's kind of easy for you to look up things, and you spend more time actually doing the exam than reading your formula sheet. Okay. And actually, one other thing that I've noticed very recently is that people are kind of copying your friend's formula sheet kind of in the last 5 minutes before the exam. So you want to make sure you're not doing that either. So you want to make sure that you kind of spend some good amount of time preparing your formula sheet. You know where everything is, and you kind of use the preparation of your formula sheet as studying for the exam. And so I'm hoping that's kind of what you use it for. Rather than something that you're going to actually try to read during the exam. That's usually not that successful from what I've seen. Okay. Okay. Any other questions on the exam or just anything that we're gonna anything that's going to happen over the next couple of weeks? Okay, all right, and so that's the exam. So definitely look forward to the study guide tomorrow, and then I'll put that out for everyone. Okay, so let's go ahead and pick up where we left off last Thursday. Okay, so last Thursday we were introducing this idea of transient or dynamic FEA simulations. Okay. And so, the whole idea behind these simulations that these are basically going to be situations that change with time. Okay, so everything we've done up to this point in the first four ANSYS activities and even with the direct stiffness problems, we've assumed that we've had a static situation that does not change with time. Okay, which is good for a lot of engineering situations. Okay. But there are going to be situations that you want to simulate where the dynamic aspect of it is important to simulate. And so it's important that we have the tools to perform these simulations. Okay. And when I say change with time, it could be any aspect of the simulation. So it could be the geometry, the boundary conditions, the positions of the parts, right? And so literally anything of the simulation can change with time. Okay. And so what I mentioned last time as well is that this area of kind of time dependent simulations is very, very rich. In fact, you can spend kind of an entire semester talking about kind of the all the nuance and all the theory behind simulating these things. In fact, it's kind of its own thing. And so, you kind of have your own kind of class on time-dependent FEA simulations or just time-dependent computations in general, just because there's so many factors that go into play. And so what we're covering in this class, of course, is going to be a very, very small fraction of that. Really is kind of just enough for you to kind of get started using a commercial software like ANSYS. Okay. And so part of this, part of using a dynamic code is, kind of having an intuition, physical intuition of what happens, or physical intuition of how physical objects respond in a dynamic way. Okay. And so that's kind of what we spent most of last time talking about. And so last time, if you recall, we talked a lot about the kind of dynamics of a mass spring system and how it vibrates as a function of time, right? And so that's going to form a good intuition of how physical objects are going to respond dynamically. Okay. What we're going to focus on today is kind of more of the practical aspects of kind of the nuts and bolts of how you actually get a dynamic simulation off the ground, what additional parameters you need to consider, what are some additional settings that you need to do, and kind of more importantly, how you actually set it up within ANSYS. Okay. Okay. And so let's start with just kind of the most obvious thing, or the most basic thing. And so, the biggest difference that you're going to see between a static simulation and a dynamic simulation is the nature of your results. Okay. In a static simulation, essentially what you're solving for is just a single snapshot, right? And so, because your situation is not changing with time in a static situation, right? You can encapsulate all the results in just a single screenshot, right? And so your results are essentially a snapshot. Okay. But for dynamic simulations, just because they change with time and the results change with time, your results are no longer a static image, but they're now going to be a series of images. And so you can almost think of it like a video. Okay. Okay. My cat's name is Sophie. Yeah, she's very cute. Okay. Right. So instead of a static image, we are going to have a video instead. Okay. And you're going to see this kind of visually in the activity that we're going to do on Thursday. Okay. And so this has kind of a number of consequences and kind of a number of different things that we have to consider. Okay. And so because our results now are going to be displayed as a video, right? Each frame of that video, you can almost think of that as kind of like a separate simulation, or like a separate static simulation. Okay. And if you've ever watched if you've ever watched a video before, right? And so depending on how many frames per second are in that video, it takes a lot of frames to generate, even just a video that's a few seconds long, right? And so what this means is essentially is that a dynamic simulation almost always is going to be a lot more expensive than a static simulation. Okay. In fact, for certain dynamic situations, and so this comparison isn't completely, accurate to this class because this it's more fluid mechanics. But notoriously, one of the most expensive simulations that you can do in the computational world is to simulate the concept of turbulence, right? And so if you take in, I know some of you may be taking aerodynamics or taken aerodynamics. And so, or you may have heard the term in your fluid mechanics course. Turbulence is very chaotic and very time dependent, right? And so it's actually impossible to simulate turbulence in a static sense, just because turbulence changes with time. There are some turbulence simulations out there and certain groups that will literally take weeks to finish. And so the simulations that we do take place on the order of seconds. And so, for just a single simulation, it takes weeks just because turbulence is so time dependent. And so, and these are weeks, not really on just your own kind of laptops or computers that you have in the lab. These are weeks on like these gigantic supercomputers with, literally thousands and thousands of processors. And so, the cost, scales up tremendously for certain things. Okay. We're not going to run such simulations. We don't have, thousands and thousands of clusters, nor do we have weeks to wait. And so, we're not going to get up to that high, but it does get very, very high in certain situations. Okay. And so that's the main thing. And so, it's when you're running dynamic simulations, you have to be a lot more careful in terms of, how you're going to devote your computational resources, because it suddenly becomes, a much, much more practical thing. Okay. Okay. And the other thing that this kind of the other kind of consequence of this is that it kind of introduces a lot more parameters that we have to consider, that are going to have a significant impact on our results. Okay. Okay. The most important of which is how we kind of break down kind of the how far apart the frames are in simulation time. Okay. Okay. And so there's in reality, there's lots of different parameters that you can set, and different combinations of the parameters do kind of the same thing. And so I'm going to focus on kind of two main parameters because these are the main ones that you have to set within ANSYS. But just know that there are other ways to kind of set these things. Okay? And so these two parameters are something called the time step size. Okay. So that's one kind of really important parameter, probably the most important parameter. Okay. And the other thing is the end time, or the total amount of simulation time for the dynamic simulation. Okay. Okay. All right. So let's go over the time step size first. Okay. And so the time step size. Okay. The time step size, typically what you'll see in a lot of literature is you'll see this displayed as delta t. Okay. And so the time step size basically defines, how much time elapses in between frames of your results. Okay. And so if we were to draw kind of a timeline, okay, of your results, okay, where each dot of this timeline is kind of a separate simulation. Okay. And so as you solve the dynamic simulation, you're going to solve for a solution each dot in this time frame. Okay. The amount of time in between each dot, that is the time step size. Okay. And so the distance here is delta t. Okay. Distance here, delta t, delta t, delta t, and so on and so forth. Okay. And so just because I'm OCD, I'm going to label each of those time points. Okay. So each point there kind of represents your simulation at a different point in time. Okay. All right, so the delta t there is a parameter that you can modify, and so you can make it really really small. And so if you make it really really small, then your time domain is going to be very well refined, or you can make delta t very large, and so that's going to make it so that a lot of time passes in between the successive frames of your simulation. Okay. And so the intuition that you should have for delta t, should kind of very closely mimic your intuition for the mesh, right? And so for the mesh, one thing that we've talked about a lot is choosing the edge size or choosing the size of your mesh, right? So the smaller you make your elements in your mesh, the more accurate your simulation is going to be, but it's going to cause your simulation to be more expensive, right? So the delta t, you should have kind of the exact same intuition. And so the smaller your delta t, okay, and so the smaller you make delta t, the less time that elapses in between the frames of your simulation. That's going to make your simulation a lot more accurate. Okay. So it's just like meshing, right? And so the smaller you make your discretization, the more accurate your simulation is going to be. Okay. But of course, that accuracy doesn't come for free. And so, usually by making delta t smaller, you're making your simulation more expensive or require more computational resources. Okay. Okay. So you can think of you can almost think of the time step size as kind of meshing the time domain. That's not quite the terminology because you don't mesh the time domain, but it's the same kind of logic. Okay. All right, question. So if I expect there to be a massive change between 5 and 10 seconds, can you refine the delta t for that specific window, or is it fixed for the entire duration? That's an excellent question. And so yeah, so one thing that ANSYS actually allows you to do is that it allows you to have kind of dynamic time stepping. And so you're not limited to just a single fixed time step size. For some softwares you are. So if you're using kind of a different finite element software or different simulation software, they may kind of force you to have a fixed time step size in between, for the entire simulation. But ANSYS can do kind of like what's called a smart time step size to kind of choose, what's the appropriate time step size. Okay. And so kind of be a bit more specific for Noah's question is, so, let's say that you're simulating a phenomenon that's going to take maybe 10 seconds overall, to complete. All right, question. So, question from Jose: would that be similar to like a mesh refinement at a location? It's exactly the same concept. So that's an excellent analogy. Yeah. And so let's say that you want to simulate a dynamic phenomenon that's going to take 10 seconds to complete. Okay. So maybe the situation we're going to do in ANSYS activity 5 is a car crash, right? And so maybe it's going to take 10 seconds for the car to make impact, bounce off, and then kind of fully settle. Okay. And so our timeline is going to look like the following. And so, on the left side, we're going to have t is equal to 0 seconds. And on the right side, we're going to have t is equal to 10 seconds, right? So t is equal to 0 is kind of the start of the phenomenon, and t is equal to 10 is going to be the end of it, okay? And so let's say that, based on this phenomenon, we expect most of the action to occur kind of at the beginning, right? And so that's generally true for a car crash. And so when you kind of hit, or just any impact problem. So when you first impact, you have kind of a lot of things happening, a lot of kind of rapid changes in kind of the energy and deformation. And so in that case, you may want a very small time step size. Okay. Okay. So maybe you have a very small time step size here. Okay. And so, when you have a lot of rapid changes in like the deformation and the stress or the strain, you want to make sure you have a time step size small enough to capture that. Okay. But once you kind of get past this, maybe the rest of your phenomenon happens on a much longer time scale, right? And so if you continue to have that very small time step size for those parts, it would be almost useless just because of you'd be kind of simulating with a very small time step size, but for each of those time steps, not much change is occurring. Okay. And so in order to kind of save on cost, maybe for the rest of the time, you use kind of a successively longer time step size. Okay. And so maybe for these here, not much change is occurring. Okay. And so when not much change is occurring, you can afford to increase the time step size to kind of save yourself on some costs. Yeah. So that's actually, that's definitely something very good that you want to do, especially for certain phenomena. Okay. So not all phenomena are being like this. Maybe for your phenomenon, you expect kind of a decent amount of change, all throughout the entire simulation. And so for that case, maybe you keep the time step size fixed the whole time. But if you have a situation where you expect a lot of rapid changes, a lot of action to occur in a short time frame, you want to kind of refine your time step size for that section. But then for the other ones, you may want to loosen it up. Okay. And so one very nice feature in ANSYS is that ANSYS can actually kind of do like a smart time step size. So they can actually choose the time step size kind of dynamically throughout the simulation based on kind of what it's observing. And in fact, that's actually the default setting in ANSYS. Okay. Okay. And so, basically the way that it works, and so, we're not going to go through the theory of kind of how it works because it actually is quite advanced. But basically, it's going to compute things like it's going to compute kind of a solution derivatives with respect to time. And then based on those values, it's going to either kind of make the time step smaller or make the time step larger based on kind of what it's observing. Okay. So actually in the activity 5, we're actually not going to select the time step size. We're going to let ANSYS kind of choose it kind of smartly. And for something like a car crash, it does actually a pretty good job of selecting the time step size that's appropriate for the problem. But I did want to make you aware of this setting because in most other softwares, you're not going to have this kind of smart time step size. And so this is something that you're going to have to choose manually, or maybe something that you're going to choose to adapt as the simulation goes along. And so whenever you are doing dynamic simulations, the time step size is a very important factor that you need to consider. Okay. ANSYS makes it really nice so that you don't have to kind of explicitly think about, but it is a very important aspect of the simulation. Okay. All right. Any questions on just the concept of a time step size? Okay. Okay. All right. So that's time step size. So that's kind of the first important factor that we need to consider. Okay. The other factor that we consider is something called the end time. Okay. And by the way, when I'm talking about time step size and end times, these are simulation times, and so this is the amount that you're actually simulating. These are not kind of real world clock times, right? And so if you set your time, so for instance, if you set your time step size to be 0.001 seconds or 1 millisecond, right? It's not that your simulation is going to complete in 1 millisecond. That's how much you're simulating, right? In terms of real world time, it may take your computer a couple minutes to actually process just 1 millisecond of simulation time, just because of the computation time required. Okay. And so ending time is kind of the same thing. So when we're specifying the end time, this is the end time for the simulation, or the amount of time, the total amount of time that you want your software to simulate. Okay. So we've actually, just seen it, right? And so in this previous example, I'm basically saying that, maybe we have a 10-second phenomenon. Okay. And so in that case, you would set your end time to be 10 seconds. Okay. It seems like a very basic thing, right? It seems like something that you don't normally think about too much. And in some situations, you don't really think about it that much. It's kind of very obvious, what your end time should be. Okay. But it does kind of pay to kind of think about it a little bit, because you want to make sure that you set your end time such that you capture all the dynamic or time dependent behavior in your system. Okay. Okay. You don't want your simulation to end early, before, all the dynamics have a chance to kind of play out. Okay. And so, for the car crash, right? And so, for a car crash, you want to make sure you set your end time so that you capture the full crash and kind of the subsequent vibrations and after effects afterwards. Okay. And so it does pay to kind of think about it a little bit, because I think if you don't think about it, then you may just kind of end up using the same default value every time, and that's probably not going to be appropriate for every situation. Okay. Another thing you want to consider with the end time is that you don't want to set it to be so high such that you're kind of simulating a lot of what I call kind of dead time. Okay. Okay. And you want to make sure you're kind of smart with your computation resources. And so, simulating dead time by itself is it's not a bad thing. It's not going to blow anything up. but it's just kind of a waste of resources, and you want to make sure that you're kind of smart using your computational resources. Okay. Okay. And so, when you're setting your end time, it's always very kind of useful to ask the question of, what phenomenon am I looking to simulate? Okay, what am I looking to capture? And how long will it take kind of realistically for that entire phenomenon to kind of play out? Okay. And then to set your end time appropriately. Right. So this is something that we will set. So this is kind of the main setting that we're going to set in activity 5. And so you want to think about, for a car crash, how long is that going to take to actually play out? It's actually going to be very fast, and so it's going to kind of take place in kind of the blink of an eye. And so what you're going to see is that our end time is actually going to be very, very short on activity 5, because it doesn't take very long for a car crash to kind of play out in real time. Okay? Because we're actually going to simulate it kind of right up, the starting point from a simulation is kind of right before impact, and so from impact to kind of final settlement, that's it's going to be a very, very short amount of time. And so sometimes you don't need to simulate a lot of time at all. Okay. Okay. Any questions on this? Okay. I covered these two parameters because these are kind of the two main things that you would set in ANSYS. Okay. In other softwares, another way that you can specify this is that a very common thing is to set the total amount of time steps that you want to simulate. Okay. And so, I know in a lot of the research softwares that I've used previously, right, the way that you simulate a dynamic, situation is that you set the time step size. So that's usually, some function of kind of what to be, good for your particular situation. Okay. And then from there, you say, I want to simulate 1,000 frames or 1,000 kind of, time steps of this phenomenon. Okay. And then based on that, your end time is computed based on multiplying the total number of time steps multiplied by your time step size. Okay. So something that was very common. So, in my previous life, well, I shouldn't say previous, I still kind of work on it, but, I simulate blood flow, right? And so blood flow usually happens on the order of seconds, right? And so, it takes a second, for most people for your heart to complete a full contraction, right? And so maybe I would simulate maybe 10 seconds of blood flow, right? So I would set my time step size to be 1 millisecond. Okay. I know that there are 1,000 milliseconds in 1 second. And so I would set the time step size to 1 millisecond, and I would set the number of time steps to be 10,000 to capture all of that phenomenon. Okay. So that's kind of a more traditional way of setting these settings. ANSYS kind of makes it kind of nice because they have kind of a lot of kind of bells and whistles that kind of make it nice for them. But just be aware that it's something other softwares may set it different. Okay, and so just kind of be aware. Okay, and so the next thing that I want to talk about is this concept of stability. Okay. Okay. So stability is actually a very common topic, or I should say a very common concern in computational, computational modeling in general. Okay, we haven't really talked about it in this class at all, just because in static situations, it's very hard to get an unstable simulation using with pure statics. But when you start to get into dynamic simulations, you may end up with an unstable solution. Okay, so now that we're doing dynamics, it's useful to kind of to have a little bit of a discussion of stability. Okay. And so in dynamic computational simulations, and so this is not just limited to ANSYS. This is for any software that does dynamic simulations. It's possible for your simulation to go unstable. Okay. And instability or unstableness, has kind of a very strict definition within the world of computational modeling. Of course, we're not going to have time to kind of go through that exact definition, but I will tell you kind of what it actually looks like, and so you'll be able to observe kind of what instability looks like. Okay, and so if you have an unstable dynamic simulation, what's going to happen is that your solution is going to start to become unbounded. Okay. Okay. And so what does an unbounded solution looks like? It looks like a situation where your displacement values or your solution starts to have kind of unrealistically high values. Okay. Right? And sometimes they even get up to infinity, right? And so if the instability kind of persists for long enough, then you're start to get like infinite deformation, infinite stress, which obviously cannot happen, right? Yeah. Right. And so, you may ask the question of, what's the threshold for unrealistically high? Well, I'll say that you'll know it when you see it. And so you're going to get deformations that are like, 5 times 10 to the 12th power, right? Okay. You don't even need units for that, right? So 5 times 10 to the 12th of anything is extremely large. So millimeters, centimeters, meters, right? It's all too big. Okay. So you'll know when you see it. And so it's not something where you think that you might miss it, right? An unstable solution is very hard to miss because it looks unreasonable, right? And so once you see it, it's kind of very obvious. Okay. And so the reason instability can happen in dynamic simulations is that you're kind of doing lots and lots of simulations kind of over and over again, right? So that's kind of what we talked about last Thursday was that dynamic simulations, you can think of it as kind of like a series of static simulations where each successive simulation depends on the previous one. Okay. And so because you're doing kind of many, many, many simulations kind of back to back to back, right? Any errors or any kind of things that go wrong, you know, doesn't really go away, right? And so it kind of persists from frame to frame to frame. In fact, what tends to happen is that these errors kind of start to build on top of each other, and they get bigger and bigger and bigger and bigger and bigger, as the simulation progresses more and more and more. Okay. And then eventually your simulation is going to get to a point where those errors have kind of piled up so much that it manifests in an unbounded solution. Okay. And so the way to fix this, or the way to kind of make sure that stability doesn't happen, there's a lot of factors that go into instability, but the number one thing that can fix instability in most cases is making the time step size smaller. Okay. Okay. So instability it's a function of a lot of things, but kind of the predominant factor that stability depends on is the time step size. Okay, and so that's kind of part of the reason why I wanted to talk about it today. And so even though ANSYS is going to do that work for you of choosing that time step size, right? So there will be times where that smart selector is not going to be smart enough, and so you may have to kind of artificially or kind of manually adjust the time step size to be smaller to make sure that you get a stable solution. Okay. For our activity, it's probably not going to be an issue. I've run this activity many times before, and I've never seen an issue with stability. But if it does happen, then the way to kind of fix it in most cases is to just kind of reduce the time step size. Okay. Okay, but I did want to mention that because that is a very common issue with dynamic unsteady simulations in general. Okay. Any questions on stability? Okay. All right. So the last thing I wanted to talk about today was two packages that actually exist in ANSYS for running dynamic simulations. And so ANSYS actually has several different packages for doing this, and it can be kind of confusing to think about kind of which ones to use in which situations. Okay. And so the two main ones that I want to talk about, the ones that kind of apply to kind of structural simulations, which are the ones that we do, is transient structural and explicit dynamics. Okay. Okay, so these are the main two packages or main two methods that ANSYS uses to run dynamic simulations. Okay, and they sound very similar. And in fact, for a lot of cases, you're not really going to notice the difference between them. But there are some subtle differences that are kind of important for certain kinds of situations. Okay, so both of these packages, or I say both of these methods, okay? So both of these methods can be used for simulating transient structural phenomena in ANSYS. Okay. Um, it's just the only difference is kind of the methods that they use to actually solve. Okay. Okay. And so this is going to be another one of those things where we're not going to have enough time to kind of discuss kind of the intricacies of the algorithms that they use. Okay. But we are going to be able to discuss kind of the differences in the characteristics of what they do. Okay. The main difference is basically how they perform the time integration or how they perform the time stepping. Okay. Okay. And so transient structural uses something called an implicit time marching scheme. Okay. Okay. Whereas explicit dynamics uses an explicit scheme. Okay. And so if you were to take a course in numerical methods or computational heat transfer, computational fluid dynamics, and so for those of you who are interested, I've talked with a lot of you over advising about 436 next semester, which is computational fluid dynamics. You are certainly going to go over the concept of these things. Okay, and so if you're interested in learning more, I would definitely recommend checking out 436 next semester. Um, but kind of the upshot is this. Okay, so for an implicit scheme, okay, implicit schemes have the benefit of being very, very stable. And so it technically still is possible to make an implicit scheme go unstable. Although depending on the textbooks, they may say that it's impossible to get implicit scheme to go unstable, which is false. So it is possible to get instability with an implicit scheme. It's just a lot more difficult. Okay, the implicit schemes are much more stable. Okay. And so because they're naturally a lot more stable, you're able to use a larger time step size. Okay. Okay. Because remember, we just talked about that stability is a big is it depends a lot on the time step size. Okay. And so if your method itself is going to be naturally a lot more stable, you can get away with using a larger time step size and still end up with a stable solution. Okay. The caveat is that this stability comes at a cost. Okay. And so in general, implicit schemes are going to be a lot more expensive time step to time step. Okay? Or I think maybe the better way to say is that it's a lot more expensive to simulate, one time step of an implicit scheme versus one time step of an explicit scheme. Okay. All right, and so a good analogy that I like to make for implicit schemes is that these are kind of almost like a quadratic element versus a linear element. Okay. So a quadratic element, per element is going to be more expensive just because you have more nodes to compute, but then that does give you some benefit of higher accuracy. Okay. Uh, and so, usually in terms of accuracy, there's not that much difference between implicit or explicit, but there is a difference in stability. Okay. And so per time step, implicit schemes are more expensive, but then, they give you more stability. Okay. Okay. And so when do you want to use implicit schemes? Okay. And so the situations where you want to use implicit schemes are for transient situations that take a long time to develop. Okay, so these are going to be cases where your end time is going to be very, very large. Okay. So let's say that you're simulating a phenomenon that takes, maybe a few minutes to develop. Okay. And so, to kind of avoid simulating, a million and one time steps, right? Another way that you can do is that you can increase your time step size so that, the time in between your time steps is large. And so that'll get you to the end time faster, or at least in less number of steps. Um, you know, um, but in order to do that, you want to still make sure your simulation is stable. So the best course of action in this case is to use an implicit time scheme with a large time step size. Okay. 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 So that's in general. That's kind of where you want where it's a little bit more beneficial to use an implicit scheme or to use transient structure. Okay. So those are going to be situations that are slow to develop. Okay. Explicit schemes are kind of the opposite in terms of kind of trade-offs. Okay. And so explicit schemes are a lot less stable. It's a lot easier to get instability with explicit schemes. Okay. And so what that means is that explicit schemes have much stricter requirements on the time step size. Okay. And so you have to use a much smaller, generally you have to use a much smaller time step size for an explicit scheme versus an implicit schemes. Okay. But the benefit that you get is that on a time step, on a per time step basis, explicit schemes are a lot cheaper. Okay, so they require a lot less computation. Okay. And so, of course, the analogy for this would be like linear elements, right? And so for linear elements on a per element basis, those are going to be a lot cheaper to compute just because they have a lot less nodes to worry about. Okay. And so in order to get an accurate result with linear elements, you have to use a much smaller mesh size or much smaller element size, and subsequently have a lot more elements. Okay, so this is kind of the same thing. Okay. And so what are the use cases for this? And so when would you want to use an explicit scheme or like explicit dynamics? These are situations where you want to use explicit dynamics in a situation where you want the time step size to be small anyway, because your phenomenon happens really, really quickly. And so in other words, maybe you have a phenomenon that takes place over the course of a second or a millisecond or something like that, right? In that situation where you want to make sure you capture, the changes that happen in that small time frame, you're going to want to use a small time step size anyway. Okay. And so in those situations where you're going to have a much smaller time step size, you might as well use an explicit method, just because it requires, much less computation per time step. Okay. Okay. And so for the activity that we're going to do on Thursday, right, what we're simulating is a car crash, right? A car crash is something that happens naturally very, very quickly. And so it's you have impact and then it's all done within a matter of, less than a second. Okay. And so the method that we're going to use on Thursday is explicit dynamics because we're going to want to use a small time step size anyway. Everything's going to happen really quickly. And so because we're using a small time step size, we have a little bit less to worry about in terms of stability. And so we can kind of get away with using the explicit scheme. Okay. But with that said, there is a lot of overlap. And so, you're gonna, if you're gonna be using dynamic simulations in a professional capacity, you're gonna have situations that are kind of in between these, right? There's not a right or wrong answer in that case, and so you can very well use an implicit method to solve a car crash too, and you can use an explicit method for something that takes place over a long period of time as well, right? And so there are things that'll work. Both of these will work for the majority of situations. It's just that some methods just work a little bit more efficiently or a little bit better than the others. Okay, and so don't stress too much about kind of choosing the right method. A lot of times you can get it to work in both situations. It's just that you may have to just wait a little bit longer for your simulation or not. Okay, but it's still going to get the job done, no matter what. Okay. Okay. Any questions on this? Okay. All right. So we have just about 10 minutes left, and so I think that's not enough time to start the next thing. So let's go ahead and end it a little bit early today. Oh, one thing I forgot to mention is that I did grade your guys' midterm projects, and so I probably should have led with that today. And so your midterm projects should all be graded on Canvas, and so you should be able to see your grade. And then what I did also was I attached the rubric that I used to grade your things as well. So you can kind of see how your points kind of broke down for each of the different sections. Okay. I tried to leave as many comments as I could. And so, for some of you, you have kind of quite a few comments in terms of kind of what I'd like to see for the final project. But actually, a lot of you guys actually just did really well. So I think the average on the midterm project was somewhere like 83 or 84% or something like that. So you guys did incredible. So that was a really good job. So, for a lot of you, I didn't really leave that much. I just said, good job, keep it up. And so, make sure you check out your midterm scores. And if you have midterm project scores, if you have any questions, definitely let me know. And I'd be happy to kind of expand a little bit more on kind of how I broke stuff down. Okay. But I did try to grade them really quickly just because I wanted to get them back to you, just so it's not on your mind while you're studying for the midterm exam. And just because, I have to kind of write the midterm exams and I have to do a lot over the next couple of weeks. So I wanted to kind of get it off my plate. And so, so the midterm projects are graded, and make sure you check that out. Okay. All right, so let's go ahead and end it a little bit early today. So thank you guys for coming today, and hope you guys enjoy the rest of your evening. I will see you guys back in class on Thursday, and yeah, I will see you then. All right, Edgar, Jaden, Mark, any final questions before I wrap it up? Okay, all right, I will see you guys. Cool. I will see you guys on Thursday.